Today we're going to look at the famous number e to the pi square root of 163. And Ramanujan in fact studied this number and noticed that it is very close to an integer. So in fact it looks like this. So it's 262, 537, 412, 640, 768, 743.999. Well, there are 12 nines before we end our string of nines. So of course, if it ends in 12 nines after the decimal point, or it starts in 12 nines after the decimal point, then it is extremely close to an integer. So I guess we could abuse notation here and say that this is approximately in the set of integers. And well, the reason that it is an integer requires some fairly deep results, and since these are deep results, they have very difficult proofs, so we won't be able to look at all of the details of the proof that this is approximately an integer, but we can at least sketch an outline for why this is so peculiarly close to being inside of the integers. And this whole thing starts with Euler in 1772, and he was studying a certain polynomial which seemed to give a lot of primes. And that polynomial, which we'll call f of n, is n squared plus n plus 41. And what was noticed here is that f of n is prime for, well, obviously not all values of n because there's no polynomial that will generate all of the primes, but for n equals 0, 1, 2, all the way up to 39. So it's prime for those first 40 cases, if you will, counting the 0th case. And I guess we could make a little bit of a chart here just to see all of these primes in action. Well, not all of the primes because that would be too big of a chart for the chalkboard, but some of the primes in action. So if we take n equal to 0, we pretty clearly get 41. If we take n equal to 1, we're going to get 43. If we take n equal to 2, we'll get 47. N equal 3 will give us 53. So those are all primes, kind of obviously. And then all the way up to, let's look at n equals 39, and that's going to give us the number 1601, which is prime. And then, well, let's look at n equals 40. And if you plug in n equals 40 into this polynomial, you'll get 1681. Now, that may look like it's prime because it doesn't immediately factor by dividing by 2, 3, or 5. We can use our divisibility checks to check that, but it is in fact not prime. This is 41 squared. So not only is it not prime, it's actually a perfect square, but that's kind of not related to what's going on here. So I guess like the next question is, well, why does this give 40 primes, and how is that related to the number 163? And in order to motivate this, what we'll do is solve the equation f of n equals 0. And so we'll solve this equation f of n equals 0, and then we'll use that to form what's called an extension of the integers that contain the roots of this polynomial. Okay, so setting fn equals 0, what does that give us? So that's going to give us n squared plus n plus 41 equals 0. But then we can use the quadratic formula, and we'll see that n is going to be equal to -1 plus and minus the square root of 1 squared, which is 1, minus 4 times 41, and then this is all over 2. Just like I said, using the quadratic formula. But you can check pretty easily that that's going to give us -1 plus minus the square root of -163 over 2. So there's that number 163 coming into existence inside of this new sort of unrelated looking problem of this polynomial that gives us lots of primes. And so now what I'd like to do is kind of start to tie together why this polynomial gives us lots of primes, what this has to do with the roots of the polynomial, and why this number up here is so close to being an integer. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up, and if you're not yet subscribed, consider subscribing. It really helps out. Okay, so along the path to understanding why this is so close to being an integer, we looked at this polynomial n squared plus n plus 41, which gave us primes for n equals 0 through 39. Then we looked at the roots of that polynomial and saw that via the quadratic formula, they were of this form, -1 plus minus the square root of minus 163 over 2. But now that leads us to look at this extension of the integers, which is z together with or adjoin 1 plus the square root of 163 over 2. And so, well, what does that, object look like? Well, that's going to be everything of the form a plus b times 1 plus the square root of 163 over 2, where a and b are both integers. So this forms something called a ring, and it's in fact an imaginary quadratic extension of the integers, if you want to use some more technical words. But it's pretty easy to check that if you take two numbers of this form and you add them, you get a number of that form. And then if you multiply them, you also get a number of that form. Maybe it's a little bit trickier to multiply them to see that you get a number of that form, but you can work out all of the details if you'd like to. And the important thing here is that our polynomial factors in this new space, in this extension of the integers. And we can write that down if we want to. We have n squared plus n plus 41 will factor as n plus 1 plus the square root of minus 163 over 2 times n plus, let's see, that's going to be 1 minus the square root of negative 163 over 2. And you might say, well, I'm just adding 1 plus the square root of negative 163 over 2, but that has a minus sign there. But that's really okay, because that's just the same thing as taking maybe b equals 1 and a equals minus 1 in this format of our numbers in this set. So anyway, we've got this nice factorization of our polynomial in this space. And now this motivates maybe a general study of extensions of integers, and we could see some more of them right here. So let's just say here we have some extensions of the integers z. And we're extending them as little as possible to contain all roots to certain polynomial equations. Okay, so the first one we'll look at is n squared plus 1 equals 0. So by inspection, it's pretty easy to see that the roots of this are going to be plus minus I, and that's going to give us this extension known as the Gaussian integers. Now, there are some important things about this extension, and that is that here we have the notion of a prime. So I'll just say primes exist. And what I mean by primes exist, that means there is unique factorization. So that means we can factor every element of these Gaussian integers into primes, and that factorization is unique. So, but that being said, not everything that's prime in the quote-unquote normal integers is still prime in the Gaussian integers. And we can see that by looking at 2, which factors as 1 plus I times 1 minus I. So 2 is not prime within the Gaussian integers. Some other things aren't prime within the Gaussian integers either. Notice that 5 can be written as 2 plus I times 2 minus I. And in fact, there's a result that says that if a prime is of the form 4n plus 3, then it's still prime in the Gaussian integers. Otherwise, it is not still prime in the Gaussian integers. So let's see, 11 is still prime within the Gaussian integers. 7 is still prime in this space. But 2 and 5 are not prime in this space. And let's see, I guess neither would 13 be, because 13 is of the form 4n plus 1. So let's see, 13 could be written as 3 plus 2i times 3 minus 2i. And that's because we can write 13 as 3 squared plus 2 squared. It's 9 plus 4. Okay, well, let's look at some more extensions. So we could look at another extension, which would be like n squared minus 2 equals 0, or I guess another equation which gives rise to an extension. So this gives rise to the extension z adjoin the square root of 2. And maybe we won't talk about if primes exist or if unique factorization exists here. I'll let you look that up. But something interesting is also going on here, and that is there are lots of invertible elements. And what I mean by invertible elements, that is things that have a multiplicative inverse. So inside of the normal integers, the only thing with a multiplicative inverse is the number 1 and the number minus 1. But in fact, in this z, together with the square root of 2, there are infinitely many multiplicative, or things with multiplicative inverses. And so there's plus minus 1, just like in the normal integers, if you will. And there's also 1 plus the square root of 2 and 1 minus the square root of 2. And well, there's a lot more too. I'll let you look up those if you want to, or play around with this to see if you can find more. But maybe just as a demonstration, let's notice that, for instance, if we have, what is it going to be? If we have minus 1 plus the square root of 2 times 1 plus the square root of 2, well then by the difference of squares formula, that's going to give us the square root of 2 squared minus 1 squared. In other words, that's going to give us 2 minus 1, which is 1. So that means those two are multiplicative inverses of each other. Okay, so let's look at one more extension before we move on. And that is, so now let's look at one more extension like this before we move on to extensions related to our original polynomial up here. And that would be n squared plus 5 equals 0, or it's related to the polynomial n squared plus 5. And so that's going to give us the extension z adjoin the square root of minus 5. That's what you get if you solve that equation. And here we do not have unique factorization. So I'll just say no unique factorization. Now I think primes still exist, but not everything that is so-called irreducible is prime. And in fact, I think I've got some videos on primes versus irreducibles, which you can check out if you'd like to. And maybe the best way of seeing this, and this is like a really famous example, is to take the number 6 and factor it as 2 times 3. And then 2 and 3 cannot break down into smaller pieces in the integers, and they also can't break down into smaller pieces in this space. But then you can also factor 6 as 1 plus the square root of minus 5 times 1 minus the square root of minus 5, just because by difference of squares, that's going to give us 1 plus 5, which is 6. And likewise, this 1 plus root minus 5 and 1 minus root minus 5 cannot be broken up into smaller parts in this space right here. Okay, so now that we've kind of motivated all of this stuff right here, this extension of integers, let's look at some extensions of integers that are related to our original polynomial equation up here, and then see how that is going to bring us back to our fact which we're trying to investigate here, which is why this number is so close to an integer. Now that we've got an idea of what an extension of the integers is, let's look at more extensions that are kind of in the spirit of this polynomial equation that we have up here. And so by in the spirit, I mean of the form n squared plus n plus p equals 0. So that polynomial equation. So let's start by noticing that this is going to give us the extension z adjoin 1 plus the square root of 1 minus 4 times p over 2. And that's just by, solving this equation right here using the quadratic formula, much as we did with this first example, and then putting inside of this new space the root or something pretty similar to the root of this polynomial equation. And then, well, let's introduce a little bit more notation. So this could also be written of the form z adjoin 1 plus the square root of minus d over 2. And this is going to be where d is equal to 4p minus 1. I'm going to write it like that because it's a little bit easier to look at, and that makes sure that d is always positive, and then p is a prime. Just if I hadn't said that before, this number p is a prime. Like right up here, this number p is 41. And now we're going to leverage some really deep results in the field of algebraic number theory, or class field theory, to bring us to our kind of goal result, if you will. And those results go like this. So if we take this polynomial expression here, n squared plus n plus p, and say that we want to restrict this to the primes where this object is prime for n equals 0, 1, 2, all the way up to p minus 2. And so that's like in the spirit of what we noticed with this n squared plus n plus 41. That number was prime for 0, 1, 2, all the way up to 39, which is obviously equal to 41 minus 2. Now, I'd like to point out, or the big point here, is that this is equivalent to having unique factorization inside of this extension of the integers. This z adjoin 1 plus the square root of minus d over 2, where that d is equal to 4p plus 1, related back to this original polynomial right here. And so let's just do this. So let's underline this in yellow and say that here, this is in line with getting unique factorization in this space. But then you might say, well, do we know the primes that make this occur, and thus the primes that make this occur? And in fact, we do, and I'll point out who proved that a little bit later. But this is if and only if our primes were from the list 2, 3, 5, and then 11, 17, and 41. And then it just stops. You might say, well, there are infinitely many primes. It seems like there should be infinitely many primes that satisfy all of these conditions, but no, there is only this list of, what is that, 6 different primes satisfying this condition. And then let's see, this is equivalent to this number d up here, which was the 4p minus 1, being inside of the following set. And that is 7, 11, 19, 43, 67, and finally 613. And there, well, we've seen our first glimpse of the number 613. Well, I guess it's not really our first glimpse here. It's related to this unique factorization kind of obviously, and the fact that that prime is equal to 41. But this number 613 is the largest one of these numbers d that make unique factorization in this space right here, or this polynomial giving us primes for those p minus 1 values of n. But I just said that these were all the numbers d, so that this z adjoin 1 plus the square root of minus d over 2 gave us unique factorization. And that's true if we require d to be of the form 4p minus 1, where p is prime, giving us p from the list that we previously discussed. But that's not true if we extend the possible values of d to be not of the form 4p plus 1. And in fact, we get this big result right here, which is z adjoin 1 plus the square root of minus d over 2 has unique factorization if and only if d comes from the following set. So it's going to be 1, 2, 3, 7, 11, 19, 43, 67, and then 163. And there's that 163 again. Let's observe that all we did was tack on these numbers 1, 2, and 3 to the beginning. And, well, observe that those numbers cannot be produced with a prime plugged into this 4p minus 1 because they're like too small, if you will. The number 3 would correspond to p equals 1, but we don't take p to be a prime. Or sorry, we don't take 1 to be a prime. The number 2 is even, which is clearly not of the form 4p minus 1. And then the number 1 would correspond to p being a half, and that's not even an integer. So in fact, if you look at these numbers, the odd ones out are the first 3 because they don't correspond to all of this business with so-called prime generating polynomials. Now, well, let's talk really quickly about who conjectured this and who proved it. And it was in fact first conjectured by Gauss, and this occurred around 1801. And then it was proven independently by 3 people. And those people were Heegner in 1952, Stark in 1967, and Baker in 1966. And these numbers are in fact called Heegner numbers based off of the first person who proved this big result here. This big result that these numbers d were the only numbers that gave us unique factorization in this quadratic extension of the integers. Okay, so now that we're like painting a picture here about how hopefully our result up here with 163 relates to the unique factorization here and the fact that this is close to an integer, let's sketch the rest of the details. Before we finish this off, I'd like to tell you about my second channel, Math Major, which has lectures for full courses at the junior, senior, undergraduate level. And in fact, that channel is kept ad-free thanks to my support on Patreon and via channel memberships. So if you'd like to help support me keeping that channel ad-free, maybe consider joining the Patreon or becoming a channel member, but there's no pressure. So finally, we're ready to look at why the number e to the pi times the square root of 163 is approximately an integer. And that requires us to introduce this thing called the analytic j function or the j-invariant. And so that is a Laurent series. Well, it's really just a power series, but we've got one term which has a negative exponent, and that is 1 over q. We'll use q as the variable here. So j of q is equal to 1 over q plus 744 plus 196,884q plus more terms. So there's going to be a q squared term, a q cubed term, so on and so forth. And here, well, q is really a stand-in for e to the 2 times pi times I times tau. And here tau is in the upper half plane. So maybe I'll just put h for upper half plane. I don't think that's really standard, but I think that's okay. And what I mean by the upper half plane is, well, inside of the complex plane, it's going to be everything above the real axis. Well, I guess including the real axis. And now here's a fact that brings this whole thing together. And this fact is a deep result, so we can't look at the details of why this fact is true, just as we didn't with our previous results, which were also deep. And that goes like this. So if D is a Heegner number, so in other words, it's in the set 1, 2, 3, 7, 11, 17, 43, 67, and 163, then J evaluated at Q sub D is exactly an integer. So it is an element of the integers. And well, what's Q sub D? Well, Q sub D is going to be e to the 2 pi I times 1 plus the square root of minus d over 2. So in other words, it is e to the 2 pi I tau, where tau is this number 1 plus the square root of minus d over 2, this thing that we extended the integers by in the previous video. And in fact, it gets a little bit stranger and better, if you will, than this, and that is not only is this an integer, but j of q sub d is a perfect cube. So I'm going to write this as m cubed for some integer m. So let's see how that makes this result right here even more astonishing than it looks. But before we do that, let's do a little bit of a calculation on what Q sub D is when D is equal to 163, because that's going to bring us back to our original case right here. So I'll just say here, what happens if Q is equal to 163, this largest Heegner number? Well, in that case, we have Q sub 163 is going to be e to the 2 times pi times I times 1 plus the square root of 163 all over 2. But now what I'm going to do is take this square root of minus 163, and since I'm using the imaginary unit in this portion of the exponent, I'll use it here as well, and I'm going to write that as I times the square root of 163. Okay, good. But now I can use the exponent rules to rewrite that as e to the pi I, so that's going to be from our 2 pi I over 2, times e to the minus pi times the square root of 163. And so obviously the 2's cancel, and then I times I is going to give us the minus 1 that we have right there. But then by Euler's famous formula, we know e to the pi I is negative 1, so this is going to give us minus e to the minus pi times the square root of 163. But now let's go ahead and plug this into our j function. So I'll just say, let's note the following, and that is that j of q sub 163, so that's exactly an integer by our result right here, our fact, if you will. But then through the expansion, we see that that is going to be equal to minus e to the pi times the square root of 163. So that's our 1 over q term. Remember that q is this number right here that we had. And then plus 744. And then plus 196,884 times e to the minus pi times the square root of 163. And that's attached to a minus sign as well. So I'll put a minus right there. And then there's going to be plus more terms. But those more terms will be something like this. So I'll write maybe the first one without its coefficient. I'll just put a big box here for its coefficient. So the next one will include e to the minus 2 times pi times the square root of 163. And now I'll put plus dot dot dot. The important thing here is that the number in the exponent is quite large and negative. And since the number in the exponent is quite large and negative, that means that e to that power is going to be very close to 0. In fact, you can check that this number right here, e to the minus pi times the square root of 163, is actually approximately equal to 3.8 times 10 to the minus 13. So it's very, very close to 0. And the rest of the terms are also very, very close to 0. So the fact that we have our goal number here, an integer here, and a bunch of terms which are very, very close to 0, and it's an alternating series, gives us some evidence to why this is in fact an integer. That's because what do we have here? Well, we've got our number plus 744 plus or minus a bunch of things that are super, super, super small is an integer. But that means that our number right here has to be very, very close to an integer. In other words, we could say the following. So we've got j evaluated at our q sub 163 is an integer. So I'll put that over there on the left. And then it's approximately equal to minus e to the pi times the square root of 163 plus 744, because we can just like disregard the rest of the terms as they're quite small. Okay, so I think we've provided some pretty good motivation for why our famous number here is famously close to being an integer. Now I'd like to wrap this up by exploring how it's not only an integer, or close to being an integer, but it's close to being a perfect cube. Okay, so now back to this fact. If d is one of these Heegner numbers, then j evaluated at this thing that we called q sub d is the cube of an integer. So that's a fact that we wrote down before. And so what we have here is that j evaluated at our q sub 163 is actually equal to the cube of minus 640,320. So it's going to be negative 640,320 cubed. So now using that this j is approximately equal to minus the square root of pi times the square root of 163 plus 744, then we can solve, if you will. I guess it's like an approximate equality, so it's not really solving. But we can move things around and we'll see that e to the pi times the square root of 163 is in fact approximately equal to 640,320 cubed plus 744. But we might as well not stop right there. We can re-express this as an approximation for pi. Let's observe that by taking the natural log, we'll have pi times the square root of 163 is approximately the natural log of this 640,320 cubed plus 744. Which means in the end that pi is approximately equal to 1 over the square root of 163 times the natural log of 640,320 cubed plus 744. And not only is this just an approximation, it's a very, very close approximation, given that this number is not just approximately equal to this integer, it's actually within 10 to the minus 13 of this integer. And that's a good place to stop.